In that case, you're using only one integral sign. Here we have to use two integral signs. So the formula says this guy is equal to the double integral with respect to the two parameters u and v. Okay, with respect to two parameters u and v, and then I need to replace everything into u and v naturally, right? So f has to be replaced by x uv, y uv, z uv. Okay, and also I have area formula. But remember, in the line integral part, we have an arc length element missing here, right? We have to add in our arc length element when we do the line integral. For surface integral, we also have to stick in one factor right here. And that factor is nothing but an area element. The area element is equal to the length of the cross product between the tangent vectors with respect to u and tangent vector with respect to v. Okay? So it's a cross product between two tangent vectors. And this one will give you so-called the area element. So in a surface area, in the surface integral, you need an area element. In the line integral, you need an arc length element. The arc length element is nothing but the length of the tangent vector. The area element is the length of the cross product between the two tangent vectors. Again, in calculus, I don't have enough time. I don't have any time to explain why this one defines an area element, but it did define the element. You can actually go to the textbook and see why this one would define a very geometric object. Okay, but overall, this is going to be the formula. Okay? And in the textbook, they actually use the notation that RU prime is equal to TU, RV prime is equal to TV, which is essentially talking about tangent vector in the U, tangent vector in V. So you can replace this guy by TU cross PV if you want. But basically, you need to do two derivatives in order to get what it is. Okay? So the formula itself does not say too much. So let's do one problem. So I have a plane. C is equal to 19 minus 3x minus 3y, where x is bounded by 1, y is bounded by 1. Okay? So originally, if I have the surface defined by a plane, and now I have two restrictions on u and v, I know this one will give me a piece of the plane. All right? This one will give me a piece of the plane. And then I want to do the integral of the easiest function possible. Fx, y, z is equal to 1. As here, f is constant 1. Okay? Which means when you replace x, y, z by u and v, the function part does not really change anything. Okay? I just want to do a surface integral of a constant function 1 with respect to this piece of the plane. Are we clear what the problem is? Mm-hmm. Questions? So we want to do a surface integral of a scalar function with respect to this piece of the plane. Okay? Now the first job I have to do is always set up your parametric equation, which means you need to introduce two parameters. So remember, we have the cylinder, we have the cone, and we have a sphere. We didn't even go through how to define a plane in a parametric form, simply because it's too simple. Okay? So in this case, if I want to introduce two parameters, I need to assign two rules for them separately. What rule do you want to assign for u? You simply put u equal x, you put v equal y, and z will be represented by u and v. Right? So the plane is pretty easy part. You just need to introduce two parameters. U is equal to x, v is equal to y, and z in this definition is nothing but 19 minus 3u minus 3v. And that's it. Right? That's the parametric equation for a plane, and I also want to have the restriction for u and v. And this restriction is coming from these restrictions for the x and y naturally, right? So u goes from goes from -1 to 1, and v goes from -1 to 1 as well. All right. So every time you want to compute the surface integral, the very first job is always to set up the parametric equation. You need two parameters, and then you need two restrictions. Okay, two equations to bound u and v, and three equations for x and y and z.
Did you make the restrictions?
The restriction is simply coming from here. X is equal to u. X norm is bounded by 1, so x is from -1 to 1. That's the same restriction for u, right? Because these two are basically the same. Okay. Now I need to compute what the r prime with respect to u is. Okay. So simply you're just doing the derivative here. So r prime of u is equal to taking the derivative separately with respect to u. What do you get? 1, 0, and -3. Okay? I want every one of you to be clear what we're doing here. We're simply taking the derivative to these three equations with respect to u, because this is the tangent vector in u. Are with me? Okay. So r prime v is equal to
0, 1,
0,
-3.
1, and -3. Okay? And then a prime here. So to be consistent with the textbook, this is TU, and this is TV. And I usually prefer to write them from the first row to the second row. So when I do the cross product, I will be very easy to do that. So r u prime times r v prime, by using these two rows, you basically have I, J, K. So you have a 3 by 3 matrix. Now with me? So I'm writing this in two rows. So when I compute the 3 by 3 matrix, it will be pretty easy to use. So basically, I, J is K. So immediately I have a 3 by 3 matrix. So I component is equal to 0 minus 3, so it's a 3. And J component is 0 minus 3, I'm getting a 3. And K component is 1 minus 0, so I have a 1. Okay? Questions? This is just a cross product between two tangent vectors. I have one small remark, not small remark. The smart of the motor is small, but it's actually a very crucial part. If I have the cross product between two tangent vectors, what exactly is this guy talking about? This is actually the normal vector of the surface. Am I right? If you have a surface, whatever surface you have, you pick two tangent vectors to the surface, and then you do the cross product. That cross product is definitely orthogonal to both of these two tangent vectors, all right? Because the cross product will produce a orthogonal vector, orthogonal to both of these two vectors. But these two vectors are both tangent to the surface. So that normal has to be normal to the surface, right? So this guy is nothing but the tangent times tangent, so you get normal. Okay? And now I'm going to plug in everything in here. So I need to compute the length of this tangent and the normal vector. So it's going to be from -1 to 1, from -1 to 1. Okay? So the function is constant function 1, so it's still 1 here. So I need to compute the length of the normal vector. So the length of the normal vector over there is going to be 3 squared plus 3 squared plus 1 squared and du dv. That's it. Right? So I have a 9 plus 9, 18, 19, square root of 19 multiplied by 2 and multiplied by 2. All right? So it's going to be square root of 19 times 2 times 2, so it's going to be 4 square root of 19.
Oh, no, 9 and 9 is 18.
Okay? So this factor is just coming from the length of the normal vector. Okay, this vector is just the length of the normal vector, which we already computed. Okay, the normal vector is 3, 3, 1. So we have this area element coming. Okay,
You can't see one.
1 is just the function. The function f is constantly equal to 1. Okay,
Why is that?
it's just the problem set up in this way.
Okay.
However, there is one special meaning when you compute the surface integral of a constant function 1. And that is going to be, what is it? If I set this constant function to be equal to 1,
Yeah.
this is nothing but the area of the surface. Okay? So when the function is equal to 1, this will be equal to the area of the surface. Okay? So essentially, if you want to know what this is talking about, okay? So we have some plane bounded by x goes from 1 to -1, y goes from -1 to 1. Okay, and this plane has some slope, right? Has a normal which is given by 3, 3, and 1. That's a normal. Okay? And this, whatever 4 square root of 19 is talking about how large this piece of the plane is. Okay, now see? It's talking about how large this piece of the plane is. Questions? So now I want to give you one more problem to practice. But before that, I want to mention the following. If I have 2 tangent vectors, I do the cross product, I will be able to produce one normal. But actually, every surface at every given point, you have 2 normal vectors. They are pointing to the opposite directions. All right? Yes? Right. You have 2 normal vectors. One is coming from the cross product between RU times RV prime. The other one is simply minus of this, right? The other one is simply -3, -3, and -1, which is pointing to the opposite direction here. So for any surface, you have a normal vector and a vector which is pointing to the opposite direction. Okay? So now I want to compute the following. So now I'm not computing for a constant function anymore. So my function is equal to 3x squared plus 3y squared. Okay? So that's the scalar function. And the surface is a sphere, which is what we already did. So I will give you the parametric form. So it's going to be 4 cosine u sine, 4 sine u cosine v, 4 sine u sine v, and 4 cosine v. So this is the parametric equation which we already derived. And also I want u to go from 0 to pi half, and the v to go from 0 to 2 pi. Okay? Immediately, what is this piece of the sphere? If I restrict u to go from 0 to pi half,
First quadrant.
we're getting the, well, v is still rotating for a whole circle. We're getting the upper half of the sphere, right? So upper half. Because u goes from 0 to pi will give you a whole sphere. Remember? So you got a ray, 0 angle to pi angle. So pi half is exactly in the middle, so you're getting a upper half of a sphere. So I want to compute the surface integral with respect to this function. Okay? This is pretty much the most complicated problem you can see for surface integral. Okay? So again, the most important element, which is actually computing this normal vector, right? Because replacing x, y, z to u and v in a scalar function, that's pretty easy. You just need to replace this one in here and that one in here. That's pretty much that is required to do. However, the computed normal vector requires a little bit more work. So we have to do this too. So RU prime, what is RU prime here? What is RU prime?
4 cosine.
4 cosine U cosine V. And 4 cosine U sine V. And
Is that a U or
sorry,
V?
it should be U. And minus 4 sine U. So the other tangent vector is equal to minus 4 sine U sine V. So 4 sine U cosine V and 0, right? So basically we're taking derivatives with respect to U and V separately. Okay? Yep. And then I need to compute RU times RV as the cross product. So I'm still writing this in 2 consecutive rules. So when I do the 3x3 matrix, I'm simply sticking an ijk in here so I can do the cross product immediately. Right? So what's the I component? This one multiplied by 0, you get a 0 minus 4 sine U times 4 sine U cosine V. So I get 16 sine squared U cosine V. Right? That's the I component. Right?
No.
So the I component is the 2x2 matrix determined right here. The determinant is 0 minus 16 sine squared U cosine V. Okay? So the J component is going to be these two multiplied together minus 0. So it's going to be 16 sine squared U sine V. And the very last one is going to be 16 cosine sine U times cosine squared V plus a 16 cosine sine U plus a sine squared V. So I have a sine squared coming from here, cosine squared coming from a product between these two. So these two will be canceled together. I get a 16 sine U cosine U. This will be the normal vector in the end. Okay? This is the normal vector. In fact, if I needed to compute the length of this normal vector, the length of this normal vector is, the normal of this vector is actually, you need to take the square root of a square, square, and a square, right? Which is not very easy to compute. However, you can do the following.